All right, here we are looking at the second big semester review, another 4 pages of problems on Unit 1 material. Um, you have the answers, which are mostly accurate. So hopefully you've been kind of checking yourself as you go through these. Nobody asked any questions on any of the piecewise functions. If you did want to see any of the piecewise stuff, from Unit 1, it was way towards the end, probably, page up in the 70s, 1, 72, 73, 74, 75, back in that area. But the first page, there were no questions on. Rational functions was a huge, huge aspect of Unit 1. We spent 2 days in January and another 2 days in February. So I can't think of anything else in Unit 1 we spent, 4 days talking about. There was a question on problem number 8, and I can think of a couple reasons why maybe somebody would ask one. One reason is because, the factorization of this top is not an obvious one. It's not a common factor. It certainly can't be a trinomial in the binomials because it has 4 terms. That also means it can't be difference of squares or some difference of cubes. It can't be factored by grouping. So what the heck are we going to do? Well, here's what I would do. I would go ahead and factor the bottom, which you pull an x out, and then difference of squares gives you x minus 1, x plus 1. Obviously, the x is not going to have a common factor with the top. The only other two that might would be a 1 or a negative 1. And so if we are going to have a whole, those are the ones we're going to test. Otherwise, if they don't work, what that means is we have 3 separate vertical asymptotes, and we can go on with our life and not worry about, there being a hole in this function. You can pretty much leave the top unfactored. However, when I try 1 and negative 1, here's what I find. 1 does not work. So, I tried 1 first because it was positive, and it gave me a non-zero remainder. But then when I tried negative 1, voila, there's your even factorization. So a little synthetic division to, keep you healthy. And so now I know that x plus 1 is a factor, and what was left, I guess I should have told you, what was left was the x squared minus the 7x plus the 10, that right there. And so that's what we did right there. That could be factored, by the way. That could be factored into x minus 5, x minus 2. I didn't do it because I just knew that factors of 5 and 2 weren't going to cancel with anything else. I wasn't going to get any more holes. So I just kind of left it like that for now. Look how much we get by just doing a little factoring. We get the domain. I now know that I have to take out a negative 1, a 0, and a positive 1. So I went ahead and did that. I noticed that 2 of those, specifically these 2, the 0 and the 1, do not cancel with any factors above. So that gives me my 2 vertical asymptotes. And then finally I noticed that I have the negative 1, boom, boom, that does cancel. And so that gives me my hole, at least half of my hole. I know the hole is at negative 1 something. At negative 1 what specifically? Well, that's where we come up here. We take the reduced function, so we get rid of those x plus 1s. It looks like in this case I did factor the top just to make it easier to multiply out, but I plug in the x value of the whole, as you can see, and looks like what I end up getting is negative 18 over negative 2, which I believe is positive 9. So positive 9 for the the y value of the hole. And once we know that, we're done with three parts of this function: domain, vertical asymptotes, holes. The horizontal asymptotes, if they exist, they don't always exist, will always come from the end behavior. The end behavior model was x cubed over x cubed, right? Power of the top, power of the bottom, which is just 1. So we're going to have a horizontal asymptote at, at 1. And now we're done with 4 out of the 5 parts. The one part we're not done with is the range. And unfortunately on these functions, the range is the one that kind of is rough. Now the first time through these rational functions, I made them kind of predictable for you. So I told you that, if there was a hole, go ahead and take that y value out. And if there was a horizontal asymptote, go ahead and take that value out. And other than that, you didn't have to worry about anything else. Just take out those 2 values and you'd be fine. But that's not very realistic, because although there are some that are very predictable like that, there are probably way more that are not. And this is definitely one of them. Because I told you there were 3 kind of crazy things that could happen. One thing is that unlike vertical asymptotes, horizontal asymptotes can actually be crossed. And if they are crossed, then we do not take those values out of the range. They are part of the range values that are hit. Furthermore, holes can be what we call covered. That means a different part of the graph hits the y value that the hole misses. But if any part of the graph hits a y value, we don't have to take it out. And finally, we have these things that I call jump gaps, which are big gaps of missing y values of a function. Well, guess what? Number 8 had all 3 of those. Here is the graph of it. And you can see, first of all, this big range of missing y values. The function never hits any y values in here. So basically between this upper local max and this lower local min, it misses every y value between. So it looks like that's from negative 25.649 to negative 0.351. None of those values, y values, are ever hit by this function. Furthermore, check this out. If you really follow this part of the graph down, what you're going to notice is it dips down and it actually passes through the horizontal asymptote and then starts coming up from below. So we do not have to take, remember we said there was a horizontal asymptote at 1. That's the red line I drew in there for you just so you can kind of see the graph approaching it. We do not have to take that out because it gets crossed. It is a value right here, on the graph. And then finally, the hole gets covered. Now remember, the hole is at negative 1, like 9. So that would have been like right about here. Remember, this is going by 5s, so this would be 10. So that's about right, just a little below 10. And what I did is, just so you could see it a little more clearly, I traced out that way and showed and let the calculator, the calculator wants to grow. I'll make it grow. The calculator, when it got to negative 1, you can see down here on the bottom, when I got there, it said, oh, there's no y value here, it's undefined. So you can't see the hole physically on these calculators, but you can trace and identify them with undefined values. So here's the thing though, even though the function misses the y value here, if you come over to this other branch of the graph, it hits that same y value at a different location. That's called covering the hole. So you do not have to take that value out of the range. And so really what it looks like in general is we just hit all y values from negative infinity up to negative 25.649, and then all y values from negative 0.351 up to positive infinity. And so that's what I wrote here for the range. Okay. It's kind of a convoluted process, and you really can't do range on rational functions without using your calculator. Now, what I noticed, and this might have been another reason why this question was asked on number 8, is that all of the values were actually accurate except for the domain. the domain was negative infinity to negative 4 or negative 4 to infinity, which makes no sense whatsoever. I believe what happened, you got to understand these solutions, there's a lot of cut and pasting and changing, cut, paste, change, cut, paste, change. It looks like number 8 got cut and pasted for number 5, and most everything got changed to be correctly, but the domain did not get fixed. So I think it was a typo. So if you asked number 8 just because you were confused by the domain, you're absolutely right. There was a typo, and the correct domain is what you see here on your screen. And there you go. So rational functions are long ones, so the rest of these should not take quite as long if you're wondering if you're going to be here watching this video for the next 3 hours. A couple more rational functions, really good practice, so keep working them. If you want a really good page with the examples and a bunch of steps on how to do these, go back to January like 24th, 25th, 26th, somewhere in there, and I have a PDF file from our lecture notes that have everything there. And then I think I repeated those notes in February when we hit the rational functions again. So page 124 in your book has some good notes, but I have way more detailed notes. There's a PDF file that you can get back on our calendar from earlier in the year. All right, finally we get done with rational functions. And we move on to even roots, and 18 here. Number 18 was the next question that was asked. And notice that even though this says even roots up here, they tried to sneak an odd root in there for you. And so what we learned about even roots is the radicand can never be negative. But what we learned about odd roots is that they don't have that limitation. And so this is just your cube root of x parent function, has all real numbers for the domain, all real numbers for the range, and usually odd roots are very, very straightforward. Well, as soon as we see that this has the odd root right there, we're thinking, oh, well then this is all real numbers, and it is for the domain, definitely and certainly. Your domain is it's as simple as that. The range though is just a little bit trickier, and it's trickier primarily because your radicand is a quadratic, and we know that with even roots, quadratics give you 2 different branches usually of values that work, or 1 limited branch. Well, here's what I did. I went ahead and factored your 2x squared plus 7x minus 15. This is how it factored. So I found the roots were 3 halves and negative 5. And so this is just a rough sketch of what that, that parabola would look like. Well, with a regular even root, right, we'd only be able to put positive numbers into it. So I'd only be able to use these 2 branches. With an odd root, I can use all the values, but the problem is the way that odd roots continue to generate infinitely many numbers going down towards negative infinity over here, oops, it didn't bend very well, did it, is because the negative x values continue to get smaller and smaller, creating smaller and smaller negative y values. This problem is going to, this function is going to have a cap on the lowest values coming out of that root, because the parabola, the quadratic equation creating it, has an absolute minimum value. Can you never get lower than that vertex there, the y value of that vertex? So here's what I did. I just graphed the parabola so you can kind of see it more accurately, and you can see the same roots we came up with, 1.5 here and negative 5 here. But you can see that down here I found the minimum. The smallest y value that this ever has is negative 21.125 at negative 1 and 3/4, it looks like there. Okay, so what that does to the function itself is it makes there be a very lowest value that the root function can ever get also, because then as we start, as the x's keep going back to negative infinity, the y's are going to start growing again because the parabola is going up again. And so what I did on this one is I actually graphed the actual function. I mean, we could have got that lowest value by putting in that negative 21 0.125, or I guess technically just put in the negative 1.75 into the full function and get it. But I actually graphed the full function, and you can see exactly what we're talking about. At negative 1.750, there's our very lowest value we ever do hit. And we do hit it. You know, we get a 0 at that value, negative 6.91. But that's why the range on this one is negative 6.91. And by the way, we hit that value, so this would be a bracket that we hit that very low value at. This is not a typical problem. This is not something I would worry about on a comprehensive final. But we saw one like that back, you know, on page like 19 or 20 when we were doing the even root assignments to begin with. Actually, I think it was actually after that. It might have been more like page 27 or 28. But whenever it was, we saw the root functions. We saw one like that, and they're kind of a pain. So usually they become graphing calculator questions. All right. So you guys are definitely picking some good problems here. After the even roots, we talk about different kinds of functions, you know, vocabulary, odd functions, one-to-one functions, no questions at all on composite functions. So apparently you guys felt, you know, for the most part, pretty good about composite functions. Now, once we got into the 30s, there were some questions about inverse functions. No questions on 30 or 31. But on 32, we definitely had a question. So let's take a quick look here at what's going on with 32. The first thing I have to do is find the inverse function. So if you look back, boy, maybe page 6, 7, 8, way back, it would have been early on that we were working with inverses. You would have found that the way to find an inverse function is to invert the x's and y's and then resolve for y. So I'm going to flip those x's and y's, and you can see that's that first step. Okay. Now, how do I solve a rational function now? Well, you can't solve for a variable in the denominator. So I'm going to get this y off by multiplying, you know, both sides by this to get this thing to cancel over here. On the other side, I have to distribute. So I distribute the x into the 3y plus 4. Now remember, I'm trying to solve for y. So what I'm going to do is I'm going to move those y's to the same side. So I think I subtracted the 3xy over here to get the y's on the same side and added the 2 over to the other side. This is the one step a lot of people would forget to do. It's you factor out the y. Now the y is solved for after I divide by the 1 minus 3x. So there's your actual inverse function there, 4x plus 2 over 1 minus 3x. It might have ended up as negative 2 minus 4x over 3x minus 1 if you had moved things to opposite sides, but it would have been the same function overall. Now, they wanted you to algebraically verify this, and so what that means is you have to put f inverse into f, and you had to put f into f inverse. So what I'm showing you here is putting that function we just came up with, f inverse, into f. And so, you know, I put this guy here and here, basically, okay? And then you can see I'm like, ooh, I don't like complex fractions, so I'm going to multiply by 1 minus 3x, and I distributed, and I got some canceling, and I had to do some distribution with the negative 2 and the 4. And I got a bunch of terms, but look, everything canceled out except for a 10x on top and a 10 on the bottom, which is x. And that's what's supposed to happen, is the function and its inverse are supposed to knock each other out, leaving you with just the x, and that is what happened. Now, you may want to see this in live action. So I saved the kind of the other direction for you here. So this time we're going to take f inverse and put f into it. Okay, so the first thing I'm going to do is go ahead and say f inverse is 4 times something plus 2 over 1 minus 3 times, let's buy a little more room here, times something. Okay, now that something I'm putting in is going to be the the original function, the f function, which is x minus 2 over 3x plus 4. So x minus 2 over 3x plus 4. X minus 2 over 3x plus 4. So I don't like having composite fractions, complex fractions, fractions within fractions. So I'm going to go ahead and take that denominator, the 3x plus 4, and multiply by both the top and the bottom. I've got to distribute here. I've got to distribute here. On the top, when I multiply the first term, this thing's going to cancel. I'm just going to get the 4 times x minus 2 or 4x minus 8 left over. On the top, I'm going to have to, nothing's going to cancel, but I do need to distribute that 2. So I'll get a 6x plus 8. Now in the denominator, when I multiply by 1, I just get 3x plus 4. But when I multiply by the second term, these guys cancel, don't they? And so I have a negative 3 times x and a negative 3 times a negative 2. Don't ever forget to distribute your negatives. So here the 8's cancel, and I'll get 10x, and here the 3x's cancel, and I'll just get 10. And so once you get in, it works out, we get x. Notice you get 10x in both of these. That's the way these rational problems always work out. You should always get the same thing, either way you do it at the very end. That reduces down to an x. Okay, so once again, you can go back and find these within the first, I think within the first 20 pages of Unit 1. I don't know the exact number, but it's in there. Moving on, we're now moving to 33 and 34, which were asked. So these, we're asking you to graphically verify them, and that just means that inverse functions are symmetric through the origin. So if I come through here and draw the origin for you, which is the line y equals x, they will reflect through that. And I kind of have a sloppy picture here, which kind of shows that relationship. Our original function is just a parabola that's been shifted 3 units over. So instead of starting here and going up, it's been shifted over to the point 3, 0, and then it's going to go up. So it'll be, I guess, more like this. So I notice, first of all, that this would not have an inverse function. Inverse functions have to be 1-to-1 to have inverse functions, because if a function doesn't pass the horizontal line tests, its inverse won't pass the vertical line test. And so that's why they give you this little condition here, like, hey, only take the negative branch of it. And so I'm only going to end up taking this part of it right here. And what that means is when I find the inverse function, and as you can see, I switch the x's and y's, and I took the square root of both sides. And normally when I take the square root, I get a plus and minus. I'm only going to take the negative root because I only took the negative branch up here. So negative square root of x plus 3 is all I end up with, which would be, going up 3 to here, and then a negative root would be reflected through the x-axis, so you kind of curve down. And sure enough, you get these curves that are reflected of each other through that, through the origin. So that's kind of what they wanted you to do. Now, if you had to algebraically verify it, I think it would be easier, because you could honestly just put one of them into the other. The square root would cancel the square, and the positive 3 and negative 3's would cancel, and you'd be done. So it's actually pretty quick. 34 is actually very similar to 32. It's a rational function. Notice how I switched the x's and y's right away. I multiplied by the y plus 3 just like I did on 32. I distributed here just like I did on 32. I got the y's on the same side just like I did on 32. I factored out the y just like I did on 32. And then there's your inverse function. Now, from that point, you could graph them on your calculator and look for that, or look at the tables, look at the table values and see that, like, AB points become BA points. You could always test it. Like, what if we threw in, I don't know, let's just pick a number of 5. Let's say we threw in a 5 here, and 2 times 5 is 10, and 5 plus 3 is 8. So 10 over 8 would be 5/4. So let's just call that 1.25, okay? So the point for our original function f was 5 went in, 1.25 came out. Now what this means is if I go down to my inverse function, I better get a 5 out if I put a 1.25 in. X's and Y's are switching places, which creates that inverse graph. So 3 times 1.25 would be 3.75, and 2 minus 1.25 would be 0.75. And I know this probably doesn't look as obvious to you as it does to me, but 0.75 goes into 3.75 exactly 5 times. And so we do get that relationship. And that would happen with every single point you try. Now, I could do the algebraic verification on this one for you again, just like I did on the last one, but it would really be the same process. So if anybody needs to see that, shoot me a message tomorrow and I can make a little mini video for you just going over that one problem. But otherwise, I think we probably are good with inverse functions for now. Moving on then. There were no questions about the domains and ranges of these logarithmic functions. So I think you guys may know the domain has to be where the argument is positive only, and the range is usually going to be all real numbers, and vertical asymptotes are going to be where the argument ends or begins. But then there started to be more questions once we got into the 50s. These were pretty simple problems where I think for the most part we were just converting things into exponentials, so this would have been 2 is the base to what power is equal to the argument, 64. Well, 64 is a power of 2, so you can kind of just think to yourself, 2 times 2 is 4 times 2 is 8, and 8 times 8 is 64, so I guess it would be 3 plus 3 is 6, so 2 to the 6th would be 64. A calculator would probably make that a little easier, but nobody really asked questions on these. But once we got into the 50s, we had to start solving equations. And the way that I try to present these to you back in Unit 1 is that there's really only 2 types of equations that you'll see. You'll see where you have logarithms on both sides, and the idea, assuming that you do have the same base, the idea is to simplify them all the way down. So you just have log of this equals log of that, and that would imply the arguments have to be equal. This equals that. The other way is you'll just have a log on one side. And so in that case, you want to simplify it all the way down and then convert it into that exponential equation and try to move forward from there. So those are really your 2 methods. These are just kind of more simple power problems where you had, exact powers. But when you started getting into problems like 54, where I have logs on one side but not on the other side. So this is where we would simplify it and then set it, turn it into an exponential and solve it. Same thing with 55. 55 was, I think, one that was asked. So why don't we take a look at that one? We've got this 4, which could definitely be pulled inside. So we'll do log of x minus 6 to the 4th power is equal to 1. Now remember, this log has no base shown, so that implies it's base 10. So what we're going to end up with here is 10 to the 1st power is equal to the x minus 6 to the 4th power. Then I guess what you're going to want to do on this one, just looking at the fourth power, I don't think we want to do x minus 6 and multiply it out to the fourth power. I think that would be a terrible, terrible idea. So I think what you're going to want to do is take the fourth root of both sides. Now, obviously, 10 is not a perfect fourth, right? I do think you might even get plus or minus when you do this, because 4 is an even root. And then you'd have to add 6 to finish this. So it'd be the fourth root of 10 plus 6 for your answer. I don't think you need to worry about the negative fourth root of 10 minus or plus 6, because that negative value, I think, would be would create a negative argument up here. Your answers can't create negative arguments, is basically what's happening. So yeah, it might still be positive. It might still be positive. Fourth root of 10. I'll have to check that one out. As far as where the negative fourth root of 10 plus 6 was still a positive value, but that's basically in essence what you're doing. Usually our numbers would not get that nasty because all of these problems would be on the non-calculator part of the test, which of course you guys will have a full calculator part of the test, but we're not really building it like that. We're not really building it like we're just expecting you guys to have calculators. I think it'll still be most of the problems you can do non-calculator. Okay, in fact, a lot of them will be way easier for you to do the way we've done them in class, not using calculators. 57 is the next problem, and so this one actually looks like you have logs on one side and not on the other, so we could simplify it, and you could, you could do it that way, but it's probably easier to just add the natural log of x, which is negative, to the other side, and then I have log of this equals log of that. And so I can, I did have to pull this 1/2 in as an exponent, which means square root, right? So x plus 3 to the square root, and that's equal to x. Well, I don't like that square root, so let's square both sides. So we square both sides, we get rid of the root, that's great, and I have this x squared. Well, of course, that creates a quadratic equation. And so I'm going to set it equal to 0, and then I'm going to be super excited when I find out that it doesn't factor simply. So that means I'm going to have to go to the quadratic formula and plug 1 in for A, negative 1 in for B, negative 3 in for C. So I won't do all the algebra on that for you. I'm assuming you guys are veterans of algebra 2, you should definitely know how to use the quadratic equation, but it would look like this: negative 1, negative b, right? Plus or minus the square root of negative 1 squared, so b squared, minus 4 times 1 times negative 3, all over 2 times 1. So 1 plus or minus. This would actually end up being 1 plus 12, right? Because you have the double negative in there. And so that would be root 13. So much for a perfect square there, right? All over 2. I don't think the 1 minus root 13 we can use. In fact, I know we can't, because that would be a negative value, which you can't have in this in this logarithm. No negatives, no zeros in there. So you're only going to have to worry about the positive root, 1 plus root 13 over 2. And if you throw that in your calculator, I think you'll find that it's equivalent to the answer from your answer key on number 57. There should only be one answer for that one, okay? All right, next question that was asked was 59. So this one I actually typed out. Isn't that nice? Well, here's what we got. On one side, I just got a log ready to work, so I'm not going to do anything with that. There's not much I can do with it, right? But on the other side, I've got a whole bunch of messy stuff. So the first thing I'm going to do is I'm going to pull my coefficients inside, as power, so it would be 6 squared, and it would be 1/9 to the 1/2 power, or the square root of 1/9. Then I'm going to use the property of logs that says when I have common bases and I subtract the logarithms, I can put those two things inside as a quotient. So the 6 squared would go on top, and the 1/9 to the 1/2 power would go on the bottom. And I already wrote it as the square root of 1/9. So I ended up with 36 over 1/3, or if you multiply by the reciprocal, 108. And that's what I do now. Now that I've simplified it down, I know that this argument has to equal this argument. So this was the other kind of problem I told you you'd see, where you don't just have logs on one side and you convert it into an exponential. You have logs on both sides, so you just simplify and set the arguments equal. And when I do set the arguments equal, I get 4x cubed equals 108, so I can divide by 4, usually with an x cubed that's not going to make you very happy. Oh, there it is. This is the type we were doing, huh? But since 27 is a perfect cube, it does make me happy. So that's how we do 59. 60 is back to a problem that doesn't have logs on both sides. It just has logs on one side. Okay, so that means we're going to simplify it as much as we can, and then we're going to convert it into an exponential function. So I'm subtracting the logarithm, so that means I'm going to divide the arguments. Okay. Now remember, this log doesn't have a base. That means it's technically 10. So that means it's going to be base to the exponent, 10 to the second power, is equal to the argument 8x over 1 plus root x, which is 100, is equal to 8x over 1 plus root x. This is not a, I mean, that part of it really wasn't bad. I hope you agree. This doesn't look promising from this point on. I mean, it looks like it's going to be a pain. And probably it's going to have to end with a graphing calculator at some point. I mean, I could show you how to try to clean it up a little bit. Maybe multiply here by 1 plus root x. So we would get 100 times 1 plus root x is equal to 8x after these guys canceled. 8 doesn't go into 100, but 4 does. So I could cancel this, by dividing by 4 and dividing by 4. So now I have 25 times 1 plus root x equals 2x. Still doesn't look like a lot of fun. I don't like the root in there for sure. I guess we could square both sides. It doesn't. 25 is not going to like being squared very much, but if we did square both sides, we would get 625 times 1 plus square root of x squared, so it would be, yeah, probably better off getting that squared by itself before you do your squaring. Probably more what you want to do. So let's go back to the step and move things around. So remember, this was 25. So 25 plus 25 root x is equal to 2x. So I would like do the 25 root x is equal to 2x minus 25. Now you could probably square them a little bit easier. You get 625x is equal to 4x squared. That'd be minus 50, so minus 100x plus 625. Alright. So now you could subtract your 625 over, and now you're finally set equal to 0, aren't you? So 4x squared minus 725x plus 625. So there you go. Yeah, like I said, I didn't think this was going to be a very promising problem, and I would bet you that does not factor. But you can go use your quadratic formula now with a is 4 and b is negative 725 and c is 625, and you'll get a couple answers. I bet you that I bet they're not very pretty. Now, I would have probably, to be quite honest, assumed this was a calculator problem way up here. And once you got to maybe, this point right here, maybe you can just set it equal to 0, zero it out, do 8x over 1 plus root x minus 100, and then graph that and use your graphing calculator in the grapher to solve it. I think that would save you a whole bunch of algebra that still is going to require a lot of hard work. So anyway, for you who asked 60, yeah, not a pretty problem, but that gives you a couple different strategies of doing it. Once again, for a cumulative final exam, you're looking for typical problems. I'm not saying easy problems, but I'm saying typical problems. A couple of the problems you asked me to go over here, primarily number 60, quite honestly, because it didn't factor, probably 57. Going back to, I think number 18 was a weird cube root one. So those weren't typical. So I wouldn't worry too much about the really freaky ones. As long as you're getting the kind of the more standard ones, you'll be in good shape. Hopefully I addressed everybody's questions who asked them. There were, about 11, I think, last night. So I think I got through them all. If you have any more, you can still come to help session tomorrow and throw them at me, and I'll try to do what I can to answer them for you. As you can see, Henry David Thoreau has some good advice. As you think about, all of your classes and what you're trying to get out of them and so on, it's not just what you achieve, it's what you become by why you're achieving those things and by what you're putting into it. All right, so give yourself a little extra motivation for all your finals, and good luck. Close it out. Definitely weird times, aren't they? Thanks for those of you that are still really sticking around and working hard. And now that I think I've posted the correct Unit 3 packet to Google Classroom, why don't you guys go ahead and start reviewing conic sections and sequences and series, and we'll work on some of those questions maybe tomorrow. If you can, join us in the morning during your little class time, last time to see each other. I'd love to see everybody, and maybe you could, wave to each other, and it would be so much fun. But otherwise, good luck, and we'll see you.